This is the 11th video in a series devoted to introductory proof writing. In the previous video, we looked at proving conditional and non-conditional statements. And when proving conditional statements, we used the direct proof method as well as proof by contrapositive. Today, we're going to look at proving conditional and non-conditional statements via contradiction. So let's look at a quick outline of a proof by contradiction, and then we're going to do a bunch of examples. So let's say we want to prove a proposition P. So P is some mathematical statement. It might be a conditional statement, it might be an existential statement, it might be something else. So what we'll initially do is suppose that P is not true. So this seems like we're kind of giving up the game. If we want to prove that something is true, why would we start our proof by supposing that it's false? Well, that's where the big trick is. What we'll do after supposing that it's false is follow that line of logic until we come up with a contradiction. So this should actually read not C and C. And that's obviously a contradiction. It's impossible for a statement C to be both false and true at the same time. But if we got a contradiction from assuming that P is false, then that means it's impossible for it to be false. In other words, it must be true. So that's how this whole thing works. Okay, so that being said, I think really we need to look at several examples, and then after which you need to get your hands dirty with some of your own proofs by contradiction. So we're going to start with a very classic one, and that is the square root of 2 is irrational. So let's see how we can do this. Obviously, we're going to use a proof by contradiction because that's the whole game today. Okay, so I like to use the following kind of language when doing a proof by contradiction, although you can come up with your own language. I like to say something like, towards a contradiction, we assume that the square root of 2 is rational. That means we can write it as A over B, where A and B are integers, and we might as well assume that this is a fraction in lowest terms. So that means that A and B share no factors, which is the same thing as saying that their GCD is equal to 1. So we'll say here the GCD of A and B is 1. So part of this equation right here is not the square root of 2 is irrational, because if we take the not of that statement, we see that the square root of 2 would be rational. But being rational means that you can be written as the ratio of integers. And then by the structure of the rational numbers, we know that we can always write a rational number in lowest terms. That's what this GCD of 1 stuff is. Okay, so now we want to take this assumption and then hopefully work it towards some sort of impossibility. Okay, so let's get started. So if the square root of 2 equals AB, then we see that 2 times b squared is equal to a squared. So we can get that by multiplying both sides by b and then squaring both sides. Okay, but look at this. We have 2 times b squared equals a squared. That means a squared is even, but if a squared is even, then a is even. So let's write this down. So a squared is even, and thus a is even. So you probably established that result in your homework exercises or something. Okay, so we know that a is even, but now we can decode a being even into an equation. So let's do that. So now let's write A as 2 times C, where C is some integer, right? So that's the definition of evenness. And then plugging this expression for A into our equation right here will actually bring us to an immediate problem. So maybe I'll extend this sentence and say, leading to 2b squared equals a squared, but that's equal to 2 times c, quantity squared, but that's equal to 4 times c squared. But notice that we can divide both sides by 2, and that leaves us with b squared is equal to 2c squared. but that means b squared is even, and thus b is even. So maybe let's just write and, so b is even. But let's see, what do we have? We have a is even and b is also even. But since a and b are both even, they're both divisible by 2. But if they're both divisible by 2, their GCD is at least 2. So we can say, so since 2 divides a and 2 divides b, we have 2 divides the GCD of a and b, right? So that's kind of the definition of the GCD. But let's recall that we started with the GCD of a and b is 1. So this ends with the statement 2 divides 1, because 1 is the GCD of a and b, but that's a contradiction. Because 2 clearly does not divide 1. 1 itself is not an even number. So we got ourselves to a contradiction, but that finishes everything off, because what did we contradict? We contradicted our original assumption way up here that the square root of 2 was rational. So if the square root of 2 cannot be rational, it must be irrational. All right, let's do another. For our second example, we've got another very classic result, and that's on the infinitude of primes. This is based off of Euclid's original proof of this statement. So let's see, our proposition is that there are infinitely many primes. So again, we're going to work towards a contradiction. Here maybe we'll use a little bit different language by way of contradiction. And I'd like to point out while we're at it that often if you're making notes or if you're doing a rough draft of a proof, you might shorten by way of contradiction to BWOC. So often when I'm writing things on the chalkboard and not writing things out in their final draft, I'll use BWOC for by way of contradiction. Okay, so anyway, so by way of contradiction, let's assume that the set of all primes is the set P1, P2, all the way up to Pn. Okay, so let's talk our way through this. So if we're assuming that there are not infinitely many primes, then that means that there are finitely many primes. But if there are finitely many primes, then we can put them all together into a finite set and index them as such. So that's exactly what we've done here. So now from this set, we're going to consider a special number. And there are lots of different proofs for infinitely many primes of different types. 4k plus 1, 4k plus 3, 5k plus 4, 5k plus 1, so on and so forth. And lots of them use a similar strategy to this. In fact, there are two main strategies for proving the infinitude of prime in special cases. And one of them is using this kind of method right here. Okay, so anyway, let's get to it. So let's consider the following number. And this number is going to cause all the problems towards our assumption of the finiteness of the set of primes. Okay, so we'll call it n, and it'll be the product of all of these primes, p1, p2, up to p little n, plus the number 1. But now, that's a natural number. And every natural number is divisible by a prime. Well, I guess we should say that's a natural number bigger than 1, and thus it's divisible by a prime. So let's find a prime dividing n. Okay, but since this set right here is the set of all primes, it must be in this set. So maybe we'll write that as which must be p sub k for some k between 1 and n. Okay, so first of all, n must be divisible by a prime, but then it must be divisible by one of these primes because this is the set of all primes. So now that we said n is divisible by pk, that means n is a multiple of pk, which means we can write n as a times pk for some a, and then we'll do kind of the calculation that finishes this thing off. So let's observe that. We can take the number 1 and we can write it as capital N minus the product P1 up to Pn. That's just by solving this equation right here for the number 1. But now capital N is a multiple of pk, so we can write it as A times pk. But then this P1 to Pn is also a multiple of pk. That's because it's the product of all of the primes, including this pk. So I'll write this as minus B times pk. And then maybe over here I'll say that B is equal to the product P1 up to pk minus 1, pk plus 1, all the way up to Pn. So it's going to be the product of all of those primes except for pk. But now we can factor a pk out, and we'll see that we have pk times A minus B. But that leads us to a problem. We have 1 is a multiple of pk. So that means pk divides the number 1. But the only natural number divisor of 1 is the number 1. So here we have thus pk is equal to 1. But 1 is not a prime. So we've ended up with pk is in this list, thus it's a prime, and it's equal to 1, so it's not a prime, but that's our contradiction. So we'll write down here a contradiction. But what was the source of this contradiction? It was way up here where we assumed that there were only finitely many primes. So thus it must be false that there are finitely many primes, and thus there are infinitely many primes. So now let's notice that neither of these were conditional statements. Let's now look at some examples of conditional statements that can be proven with a proof by contradiction. Now let's look at proofs by contradiction for conditional statements. But in order to do that, let's recall what the negation of a conditional statement is. So not P implies Q is the same thing as P and not Q. So we made a truth table earlier to establish that logical equivalence. Okay, so now let's say we want to prove the proposition if P then Q, which is the same thing as this conditional right here. So if we want to do it via contradiction, we'll suppose that this conditional is not true. So in other words, we will suppose that P is true and Q is false. And then we'll do calculations with that setup. That's what happens in this box, which will lead us towards a contradiction just like we had before. So we'll have some statement is true and some statement is not true. So let's recall earlier we had contradictions like 2 divided 1. So 2 clearly does not divide 1. And we had another contradiction where some number was simultaneously a prime and it was equal to 1, but that's not possible. So I'd just like to do a little bit of a remark down here. So if C looks like P or Q, then maybe this proof could have really been done with a proof by contrapositive. Now, some instructors are really strict about only making a contradictory proof when a contrapositive proof is impossible. I'm not that picky, but just be aware of the instructor that you have. I guess the best case is that C is unrelated to P and Q. That's really the mark of a contradictory proof that was not a contrapositive proof in disguise. Okay, so let's look at an example. So let's prove the following conditional statement. If A and B are integers and A is bigger than or equal to 2, then A does not divide B, or A does not divide B plus 1. Okay, so just to maybe write this out, this statement here, which I'm underlining, would be our statement P. This statement here, which I'm now underlining, would be our statement Q. So we want to initially assume P is true and Q is false. So let's do that. So let's first notice that we're working towards a contradiction. So I'll put BWOC by way of contradiction. Now in your final write-up of a problem like this, you'd want to write those words out. Okay, so by way of contradiction, let's suppose that A and B are integers where A is bigger than 2 or equal to 2 and A divides B and A divides B plus 1. So let's recall that when negating Q, which is an OR statement, that's going to turn the OR statement into an AND statement. Okay, so now let's use the definition of divisibility to rewrite this a little bit. So thus, we have B is equal to A times M, and B plus 1 is equal to A times N. And that's going to be for some M and N, which are integers. Now here's where we cause the problem. So let's do our subtraction of B plus 1 and B. So we have 1 is the same thing as B plus 1 minus B, but that's going to be the same thing as AN minus AM, but that's going to be the same thing as A times N minus M. But that means we've got an integer A which divides 1. But there are exactly two integers A that divide 1, and that's plus 1 and minus 1. So thus, we have A equals plus or minus 1. So let's see what we have. We have A is plus or minus 1, and A is bigger than or equal to 2 up here. But that's a contradiction. So I'll just put these two arrows going towards each other. That would be read as that is a contradiction. And that finishes this proof. And now we'd probably like to do a little bit of a review of this proof to make sure that we couldn't do a proof by contrapositive. And in fact, this one is a little bit on the edge. I'll let you check if you can do a proof by contrapositive, but I think a proof by contrapositive would not lead to A being bigger than or equal to 2. It would in fact lead to A being bigger than or equal to 2 or A being less than or equal to -2. So I would say this problem lies somewhere in the middle right here. So C does look like P or Q, but if we try to do the proof by contrapositive, which like I said, I'll let you do, we don't end up proving not the original statement. We end up proving like something similar to it, but that's a little bit weaker. So that being said, it's also not one of these best cases, which is to be expected because not every proposition that you try to prove will fall perfectly into one of these two cases. And that's just something that you have to work with. Okay, now let's move on to biconditional statements. Now we're going to look at biconditional statements, but luckily this is really just proving two conditional statements in a single proof. And we're armed with a couple of different strategies for proving conditional statements, so we should be good to go. But that being said, let's look at a quick outline just for good measure. So let's say we want to prove the biconditional statement P if and only if Q. That means we need to prove P implies Q using any method that we want, and we need to prove Q implies P using any method that we want. And that's really all there is to it. Okay, we're going to do two examples. The first one is actually something that we used previously in the video, but that being said, I think it's nice to see written out. So we'll prove that the integer n is even if and only if n squared is even. So I like to point out which direction I'm doing one at a time. And so I'll start by saying, okay, I'm going to go in this direction first. So I'll put the implication arrow and put a little box around it. Now, keeping in mind good proofwriting etiquette, which you were assigned to read at the end of the last video, you'd want to put this into a sentence in your final draft. And this is something really important to stress, is that your first draft of a proof should not be the same as your final draft. And your chalkboard draft and your chalkboard notation needs to be translated into final draft notation. Okay, so that being said, let's do this forward direction first. And we're going to do this with the method of direct proof. So let's suppose that n is even. Okay. But what does that mean? So by definition of n being even, we have n is equal to 2k for some integer k. So that's the definition of evenness. But now, thus, n squared is equal to 2 times k quantity squared, which is the same thing as 4 times k squared, which is the same thing as 2 times the quantity 2k squared, which is even. And there we've done it. If n is even, then n squared is even. So now let's do the reverse direction. So I'll just put a little box and then the arrow going the other direction. And since we just talked about a proof by contradiction, let's do it that way. That being said, a proof by contrapositive is also a good choice. And actually, in the end, perhaps this proof by contradiction really could have been written as a proof by contrapositive, but we'll see that at the end. Okay, so for the reverse direction, what do we need to suppose? Let's suppose that n squared is even and n is odd, right? So if we're going in the reverse direction, we want to prove that if n squared is even, then n is even. So recall that the negation of that implication would be this kind of setup right here. Okay, that's good. So now let's write n as 2k plus 1 for some integer k. And we'll simultaneously write n squared as 2 times maybe l for some integer l. Okay, so we're able to do that by the assumption that n squared is even and n is odd. So now from there, let's do our calculation. So let's put a heading on that like observe. So let's do 0 equals n squared minus n squared. But now let's use our two versions of n squared. So this is equal to 2k plus 1 quantity squared minus 2 times L, where the first version of n squared is taken from this expression, n is 2k plus 1, and the second is taken from our expression for n squared as an even number. Okay, so now let's do a bit of calculation. That's going to give us 4k squared plus 4k plus 1 minus 2l. But now notice that we've got 0 on the left-hand side, and we have even plus odd minus even. That's definitely an odd number on the right-hand side. That being said, in a previous video we learned about congruence mod n, so let's maybe simplify this with the language of congruence mod 2. So this right-hand side is congruent to 1 modulo 2. So if you need to review that definition, now would be a good time to do that. So let's see what we ended up with. We have 0 is congruent to 1 mod 2, but that's a clear contradiction. So a contradiction. Recall that numbers are congruent mod 2 if and only if their difference is a multiple of 2. But the difference of 0 and 1 is not a multiple of 2. So that contradiction finishes off the proof of this backwards direction. Okay, so that being said, I think a proof by contrapositive is much better here, but I think doing this proof by contradiction is a nice illustration, especially going down here to the end and using this newer technology of congruence mod 2. Okay, so now let's do another. This next example will also use the notion of congruence mod n. And I'm also going to introduce a little bit of shorthand that perhaps you haven't seen yet. So we will start by supposing that we've got integers a and b. And then from there, we'd like to show that a is congruent to b mod 15 if and only if a is congruent to b mod 3 and a is congruent to b mod 5. And the shorthand that we're introducing is this IFF for if and only if. So again, this is something you would write in your notes or on the chalkboard, not in a final solution. Okay, so let's go and start maybe with the forward direction. So let's suppose that A is congruent to B mod 15. And we'll hopefully be able to prove is that A is congruent to B mod 3 and mod 5. Okay, so let's decompose this into a definition. So thus, 15 divides A minus B. That's the definition of congruence mod 15. So A minus B is equal to 15 times n for some integer n. Again, that's the definition of divisibility. So we had a twofold uncoupling of our definition. First, from congruence mod 15 to divisibility to this being a multiple. So that's cool. Okay, so now let's go from there, keeping in mind that we're trying to get to congruent mod 3 and congruent mod 15. Okay, so let's see if we can do this all at once. So let's note that a minus b is equal to 3 times 5n, and a minus b is equal to 5 times 3n. So that's obviously the same thing because of commutativity and associativity of multiplication, but writing it in this first way, we see that a minus b is a multiple of 3, and writing it in the second way, we see that it's a multiple of 5. So now we would maybe say that 3 divides a minus b and 5 divides a minus b. Thus, a is congruent to b mod 3 and a is congruent to b mod 5. Again, note what we did here is we unpacked the definition, did a tiny bit of a calculation. It was really just the factoring of 15 into 3 times 5, and then repacked the definition. Okay, so that finishes the proof of this direction. So now let's do a proof of the other direction. Now let's look at the reverse direction. Now I think we can do this with a direct proof as well. So let's start by supposing that a is congruent to b mod 3 and a is congruent to b mod 5. So here I use this SPS as a shortening for suppose sometimes. Now let's unpack these definitions into equations. So thus 3 divides a minus b and 5 divides a minus b. So a minus b is equal to 3m and a minus b is equal to 5n, where m and n are appropriate integers. Now, let's maybe cut out the a minus b bit and notice that this means that 5 times n is equal to 3 times m. But that means the left-hand side is a multiple of 5, and thus the right-hand side is also a multiple of 5. Now, technically we're using the fundamental theorem of arithmetic here, but I think that's kind of okay here. But 3 is most definitely not a multiple of 5, so that means that m is a multiple of 5. So via that, we can write m as 5 times k for some integer k. Great. And that's because 5 and 3 are both primes, and thus 1 is not a multiple of either. Okay, great. So we've got m is equal to 5k. Now we plug this version of m back up here. So I would maybe write that as, notice that a minus b is equal to 3 times m, which is now equal to 3 times 5k, which is equal to 15k, which leads to a congruent to b mod 15. So I skipped maybe an intermediate step where I said that 15 divides a minus b, but I think that's okay here. So that finishes this reverse direction, which finishes this proof. Okay, so now we're going to end with a few assorted results. Like I said, we're going to finish with a couple of assorted results. And this first one is an existential statement. So we'll prove that two numbers exist that satisfy some rule. We won't show that they're unique though. And in fact, in this case, they are not unique. And so this is a really famous formula called Bezout's formula, or Bezout's lemma. So it says that if we've got natural numbers a and b, then there are integers x and y such that ax plus by equals d, where d is the GCD of a and b. So in other words, given two natural numbers, you can always write their greatest common divisor as a linear combination of those natural numbers, where you think about linear combination in terms of what you learned probably in a linear algebra class. Okay, so the proof of this is super classic. So let's get going. So let's consider the following set. So I'll call that set S. And it'll be everything of the form AU plus BV, where U and V range over all integers. And then we'll take that and intersect it with the natural numbers. And so now let's note that the number a is in S. Well, so notice that we get the number a by taking u equal to 1 and v is equal to 0. And since a is a natural number, it's both in this set and that set over there. But what that really tells us is that S is non-empty. So we have a non-empty set of natural numbers. So now let's recall earlier we talked about something called the well-ordering principle. And the well-ordering principle allowed us to take any non-empty set of natural numbers and choose a smallest element. And that's exactly what we're going to do here. So by well-ordering, S has a smallest element. And what will we call it? Well, based off of this up here, we'll call it D. So D is equal to the minimum of S. But since S is everything of the form AU plus BV, that means D is of this form too. And so we'll take the numbers that produce D to be equal to X and Y. So we'll define integers X and Y such that D equals AX plus BY. So in other words, X is the U value that produces D, and Y is the V value that produces D. Okay, good. So now from here, what we'd like to do is show that D is in fact the GCD. So I think this is a perfect place for a subclaim. So let's put that here. So claim D in fact is equal to the GCD of A and B. So let's recall, in order to prove that, we need to show that it's a CD, in other words, a common divisor, and then we have to show that it's the largest such common divisor. So let's first show that it's a common divisor. And we'll do that by dividing A by D and show that we get a remainder of 0. And since A and B are playing symmetric roles here, we only need to check it for A. The B is similar, which we'll write at the end. So now let's use the division algorithm with D and A to write A equals D times Q plus R, where R is between 0 and, let's see, D. Great. So again, like I said, that's the division algorithm. And now let's notice if R is equal to 0, we are done, because that implies that D divides A. And then similarly, D divides B. So by way of contradiction, let's suppose that D is not 0. So by way of contradiction, suppose I meant R is not 0. But now let's solve this equation for R. So let's note now that R is equal to A minus D times Q, but that's equal to A minus AX plus BY times Q, where we wrote D using that linear combination of A and B. But now we can collect terms and then see that we get A times the quantity 1 minus QX, and then plus B times QY. But that's an element of S, because it's a linear combination of A and B, and that's what it takes to be an S. You have to be a linear combination of A and B, and you also have to be a natural number. But if R is not equal to 0, that means it's bigger than 0, which means it is a natural number. But that's a problem, because what do we have now? We have R is strictly less than D, and we have R is an element of S. So that means that R is in S, but it is smaller than the minimal element. But that's a contradiction. You can't be smaller than the minimum of a set. So here we've reached a contradiction. And so that contradicts this possibility right here, the possibility that R is not equal to 0, which means that R really is equal to 0. But if R is equal to 0, then we have D is in fact a divisor of A. But then, like I said, D being a divisor of A and showing D being a divisor of B is really exactly the same proof. So that means we know that D is a divisor of both A and B, which is the first thing we need to prove when we show that D is the greatest common divisor. Okay, so now let's show the greatest part. So along the path of showing that D is the greatest common divisor of A and B, we've shown that D is a common divisor of A and B. So let's recall that we really only proved this case right here, that D is a divisor of A. But the case when D is a divisor of B is exactly the same. We could use our similarly approach in that case. Okay, so we have it's a common divisor. Now we need to show that it is in fact the greatest common divisor. So let's suppose that we have another common divisor. I'll call it C. So C divides A and C divides B. Okay, great. But what does that mean? That means that A is equal to C times some number, maybe we'll use the number Z, and then B is equal to C times another number which I'll call W, where Z and W are integers. But now let's look at D. So maybe we'll do the following calculation. D is equal to AX plus BY from what we had up here. But now that'll be equal to C times XZ from this expression for A plus C times YW from this expression for B. But that's equal to C times some stuff. That stuff is XZ plus YW. So we have D is equal to a multiple of C, which is the same thing as saying that C divides D. But that's exactly what we needed to prove the greatest part of the greatest common divisor. And that finishes off this proof. Okay, good. Let's do one more. So we're going to finish off with a really classic result. And that is there exist irrational numbers, x and y, such that x to the y is rational. So I think that's pretty cool. We're going to give two proofs here, a non-constructive proof and a constructive proof. And I guess like a non-constructed proof might have some logical issues depending on how you feel about the law of excluded middle. But that's some really kind of hardcore logic stuff that we're not going to worry about so much. Okay, so for our non-constructive proof first, so this is going to break down into two cases. And it's so quick. Notice I don't have much room here, and that's because I won't need much room. So our first case is, what happens if the square root of 2 to the power square root of 2 is rational? So perhaps that is a rational number. And if it is, then we are done. Because we've got an example of an irrational to an irrational which is rational. Okay, cool. So what about case 2? So case 2 is what happens if this number is not rational. So if this number is not rational, then in fact we can raise it to another number which is also irrational to produce something that's definitely rational. So let's do that. So let's note that if we take the square root of 2 to the square root of 2 and raise that to the square root of 2, then by our assumption we have an irrational to an irrational. But by exponent rules, this simplifies to the square root of 2 to the 2 power, which is 2, which is rational. And we're done. So either way we have it, we have an example of an irrational to an irrational, which is rational. So here we're going to actually define numbers x and y. So let's set x equal to the square root of 2. Notice that is irrational by earlier in the video. And then we'll set y equal to the log base 2 of 25. And this is irrational by a homework exercise. And then from this setup, now let's observe that we can take x to the y, which is the square root of 2, all to the power log base 2 of 25. And we can write this as the square root of 2 to the power 2 log base 2 of 5. But then this 2 will cancel that square root of 2 down to a 2, and that leaves us with 2 to the power log base 2 of 5, which is clearly equal to 5, which is a rational number. So we've got an explicit example of an irrational to an irrational, which is a rational. Okay, so now I'm going to leave you with a couple of warm-ups. So I'm leaving you with 4 warm-up exercises. The first one is the gap in that proof that we just saw, and that is to show that the log base 2 of 25 is irrational. Next, show that there are no xy integers xy, such that 4x minus 6y is equal to 1. Next, suppose that a and b are natural numbers and show that a is equal to the GCD of a and b if and only if a divides b. And finally, say you've got an integer n, then you want to show that 2n squared plus n plus 5 is even if and only if n is odd. And that's a good place to stop.